I think we're good. So let's get started. I was just telling people again the AI adventures of this thing. There is a horse setting on it. So, right, the first couple of lectures I had tried to locate my face, but then if I turned around, it didn't locate me anymore. So I found there's a body setting. That is the one I'm using now. Works. When playing around with this, I also found there's a horse setting. So you can actually make the thing only focus on a horse. So of all animals that you want to measure with this thing, apparently a horse is singled out by the makers of this machine. And I just wonder how many people, buy a thing because they want to record horses.
It works better if you use that and put on a horse mask.
Yeah, they've already said this, that maybe next year I should just wear a horse uniform. It's around Halloween time that this course runs, so I might as well just put on a horse costume, or I don't know, make some horsey noises every now and then. Do a little bit of a every now whatever horses sounds horses make. Okay, let's get started. As we already discussed in the previous weeks, we already have everything that you want or need to know about special relativity, namely, what are inertial systems? How does one then get the laws that tell you the amount of time and distance in between two inertial systems? Those are Lorentz transforms, which in special cases, as you know, reduce to the Lorentz contraction or the time dilation. But there is not much more. Literally, I mean, this is everything that you can do to measure something in one frame and mathematically transform it and how things should look in another frame. So what else is there to do? And the answer is, what we have not looked at all is when you start to interact with stuff. Right now, everything that we've done is something happening, like spaceships or exploding stars or, I don't know, running horses or something like that, but everything is always passively working in the background, and somebody measured in this frame, you have to translate to how it looks in the other frame. But us interacting with the stuff that is doing the moving, that part we haven't done yet. That's what we're going to do in the final 2 weeks. We're going to do the mechanics, so to say, of special relativity. And just to already point out why we have to do mechanics, we cannot use our previous mechanics. Previous mechanics, for instance, being Newton's second law. Right? Newton's second law for constant mass would look something like this, or the sum of forces, something like that. Not something like that, it's exactly like that. But you know that this cannot be true for special relativity, because if you were in a situation where there's a force, and the force is acting on an object, a mass, maybe indefinitely or maybe a finite amount of time, in principle you're allowed to get a constant acceleration. But if you have a constant acceleration, then that means things can speed up and speed up and speed up some more, and you can do it indefinitely, and maybe you'll find yourself with things going faster than light. Is that allowed? Well, we haven't quite shown yet that it's not allowed. That's one of the things we will see today. But there were strong hints that things cannot go faster than light. Because if things go faster than light, at the very least you run into trouble with the gamma factor, the Lorentz factor, being imaginary. And that is something that might be an issue. Again, it's not a proof, but we've seen strong hints that things cannot go faster than light. We've seen other hints too. We found that there's a light barrier, right? In the Minkowski diagram, that's a 45-degree line. We found that you cannot go from one side to the other if you yourself cannot go faster than light. That was one of the things we saw a few weeks ago. In the tutorials there was some exercise on that. So the speed of light seems to be a barrier. But all of that is suggestion. We have to prove that stuff. And that's what we're going to do with mechanics. But if you will already accept from me that you cannot go faster than light, masses, then that means that Newton's second law is in some regime going to give you the wrong conclusions, because hey, constant force means constant acceleration, and if you keep it up long enough, things will go faster than light. So we know that mechanics in the Newtonian way is not correct yet. Right? That's a quick and dirty way of seeing why Newtonian mechanics has to be replaced by relativistic mechanics. There's a little bit more to it too. You have to think a little deeper here, namely an acceleration, of course, is the amount of distance traveled per amount of second, and that itself per amount of second. But as you know, distance is not a fixed number. I mean, it changes from inertial frame to inertial frame. But the amount of seconds also changes from inertial frame to inertial frame. So you know that this object in its totality is also, careful. Yeah. Okay, still tracking me, good. He even shook his head for a moment. So, as you know, that's not the guy. Okay, good. The acceleration is itself some combination of distance and durations, but those numbers are different between inertial systems. So Newton's second law doesn't take care of that distinction at all. It didn't have to, because in Newton's mechanics, Newton's laws of physics, time is the same in all inertial systems. So on a somewhat deeper level too, you can see that this law has to be replaced with something more, more general, so to say. Well, that's our goal for today and for next week. We're going to do this in 2 steps. I'm going to derive the laws of relativistic mechanics this week in a very simple case where you leave things alone. So somebody gave a rocket ship a boost or a push, and we're going to see, well, what is its energy, what is its momentum. But we're still not going to touch it, but we're going to lay down the mathematical foundations. And then next week, we're actually going to put in that we ourselves are allowed to start pushing and pulling on stuff. So it's a 2-step process, so to say. So today, only, well, looking at things that are moving and understanding how energy and momentum works. Next week, if we ourselves start pushing and pulling on stuff. The today version, we're going to do in 2 ways. First, we're going to derive this directly from the Minkowski line element, the laws of energy and momentum. That's our main goal, to show how that works. But later in today's lecture, I will show you a different mathematical technique. And this might be new to some. It's called Lagrangian mechanics. Trying to look at faces. See some people nodding along, some people scowling-ish. For the people who are not familiar with Lagrangian mechanics, it's a way of doing mechanics, as in understanding how things interact with each other, but in a way that is much more effective than your usual Newton's laws that I had over there. For some people that might be new. Some other people might have seen it in different courses. I'm going to introduce it in this course. Not a full course in Lagrangian mechanics, but enough for you to understand how you do this relativistically. If we go through that process, we will find exactly what we're also going to find if we get it directly from the Minkowski line element. Yes? So if you want, there's sort of a double learning goal for today. First of all, what are the laws of mechanics? And the second one is, and how do you get it from Lagrangian formalism? That's the plan. I propose we get started. Let's find the expression for the energy and the momentum of some mass flying about in an inertial frame under the laws of special relativity. Let's write down the Minkowski line element. You will remember this because we derived this already some weeks ago. So there's nothing new, there's no new physics there, this is what we saw before. The amount of time is different between inertial frames. The amount of distance is different in inertial frames due to time dilation and Lorentz contraction and Lorentz transforms. But this particular combination always stays the same. It's an invariant. And in fact, let's actually give the invariant its own symbol. So this number, whatever comes out, be it 14 or 7 or minus pi, whatever the number is, it's a number that's shared between all inertial systems. But that number itself, we designate by d tau squared with the c squared. You remember what d tau was, yes? It's proper time, the amount of time that passes for somebody who sees something, some 2 events happening at the same location. You can see why that is the case, because if the unprimed observer here happens to be the person for whom the 2 events happen at the same location, then by definition for that observer, dz is 0, dx is 0, dy is 0. And what remains is this, and then all the way back in week 1, we call that amount of time proper time. So if you open up your books, you will typically find that the invariance of the Minkowski line element is not written as equals invariant, but is written as equals minus c d tau squared, because it is. So I'm going to do that here too. Again, no new physics, everything that we already knew before. This is the Minkowski line element, all derived before. But here's my little trick. I'm going to take this rule and I'm going to algebraically play with it for a little bit. I'm going to multiply this, I'm going to divide this by particular numbers, play, and at some point I will end up with expressions for energy and momentum. But here's the key part. I'm only allowed to multiply or divide or whatever I do to this expression with numbers that themselves are invariant. If I'm going to multiply this with a number that is not the same between inertial systems, then this equality sign will not hold anymore. Yes? And you will remember the principle of relativity that states that you want your laws of physics to be such that they hold in all inertial systems. So if I want to turn this into some energy momentum relation, I better only do stuff with this invariant equation that gives you the same outcome in all inertial systems. The only things that I get to do with it themselves should be things that are the same in all inertial systems. Otherwise, I break my invariance. Meaning that I will get expressions maybe for energy and momentum, but only expressions that hold in some inertial systems and not all. So I can only manipulate this by using numbers that are invariant. But we know a couple of these numbers. The speed of light is one. The speed of light is invariant. All the way back in week 1, that was by postulate, because this is how people found this originally from Maxwell's equations. So the speed of light I can play with. In week 2, we actually derived that C is invariant, not by postulate, but by mathematical result of inertial systems. Are there any more numbers that are invariant? Numbers that will not change from one inertial system to the other?
Mass.
Or I hear mass? Anything else?
Distance is not in the travel direction.
Sorry, what's that?
Distance is not in the travel direction.
That's a good point. Sure, if I'm going to do a coordinate transform between inertial systems that only move in x direction, everything in y and in z directions will not change either, because Lorentz contractions only work in the direction of motion. You're absolutely right. But then we have sort of semi-broken the principle of relativity, because then we've limited ourselves to systems that only move with this in x direction with respect to each other, and we want to keep it a little bit more open. But you are right. If we decide to only coordinate transform in x direction, then everything in z and in y is also invariant. But let's make it isotropic, that in all directions I want my laws to still hold. Okay, so let's make a small list of invariant numbers, because I'm going to need those numbers to play around with this object and then find some invariant expression for energy and momentum. Actually, we can ask for that.
What am I?
Invariant numbers.
Invariant numbers. Well, the speed of light. But
You want me to give more?
Well, there's one on the board right now. I mean, the Minkowski line element, d tau, is invariant. So we can also play with the amount of time as measured by somebody who sees everything from one location. But a very important one is, yes?
Mass?
Yes, the very important one is mass. We played this out before, yes, this is all agreed upon, this little one-on-one discussion. Mass is an invariant. And here is where I would like to pause for a moment, because sometimes mass is explicitly stated in some books, and I should say the not so professional books, that mass is not invariant, that kilograms increase if you go with a high velocity. This is a very often heard statement, for instance, to explain why things cannot go faster than light. Because if things go really fast, then something that is 90 kilos becomes 100 kilos, becomes 200 kilos, 700 kilos, 1000 kilos. And the more kilos it has, the more difficult it is to accelerate it even more. And if you keep that up, at some point the mass will be so big that you cannot push it any faster, and that fastest speed that you get is the speed of light. That is one way that sometimes the speed of light as the highest velocity for objects is explained. I do this because it's not true. And by this I don't mean that it's sort of true, but I would like to state it differently. It is literally not true. Mass does not increase with high velocities. It's sort of an explanation thing that very quickly breaks down, and I want to get this out of your system, if you had it there, as quickly as you can. Mass is invariant. A very quick way of coming to that conclusion is the following. If I were to put here a scale, and I would place myself on it, then I would say a number, which I'm sorry to say is about 90 kilos. 90 kilo scale. Now then the other guy comes along, and in their frame, if you believe the mass becomes bigger with high velocity, in their frame, if they move with respect to me, then I'm not standing still, and then the story goes, oh, that means his mass is not 90, it becomes bigger. Okay, so does the scale now give, say, 100? I mean, there's literally a little dial on the scale that says 90 or 100. And for me it says 90, and for the other guy it should say 100. First of all, how does the scale know that that the other guy was running along? How would it know? What kind of causal connection is there? Already there's something wrong there. Secondly, very important, that person and I disagree. Because if you ask me how many kilos the thing says, it says 90, but yes, the other guy says 100. Well, it cannot be 90 and 100. Yes? That's an extremely simple but extremely important conclusion. Mass really, really, really doesn't get bigger if you move with respect to it. Now, I've made a little thought experiment to drive the point home. It's as follows. So this is a variation of what I was just saying. Let's put a mass on the string. And let's make the string such of a material that can only hold up to 100 newtons of weight. I'm just making up a number, right? The material is such that it can have 100 newtons. If it's more than 100 newtons, the string breaks. This is the material property of the string. Okay? Let's put a button there. The button gets pressed, something blows up. In my own lecture notes I called it the Eiffel Tower, but take your pick. It's the Eiffel Tower. Okay, well, we're in luck because, hey, this mass is only 10 kilograms, and 10 kilograms close to the Earth gives you a weight of about 98 newtons or so. The string tension will hold, thing will not break, button will not be pushed, Eiffel Tower does not explode. But then the other guy comes along and they start running, and they say, well, the story goes, in my frame this mass is not 90 anymore, but it becomes, is not 10 anymore, it becomes 20 or 30 depending how fast you're running. But that means in that frame, all of a sudden the string would break and the Eiffel Tower would explode. Now that is not the kind of, well, you know, in different frames, time and space looks different. Well, in one frame the Eiffel Tower explodes, and the other one it doesn't. That is a real contradiction. Not one you can brush away by saying, oh, loss of simultaneity or something like that. No, no, no. This is really a physical distinct difference. You can try to argue your way around this, but I've made this example such that you can't. Right? You could, for instance, say, but wait a minute, what? For the other person, sure, this guy goes from 10 kilos to 20 maybe, but maybe the string tension becomes bigger too, so it still holds. Doesn't work. Because the string is perpendicular to the direction of motion. It doesn't feel anything at all. It's independent of the Lorentz transform that was made. So the string is kept completely the same, including its material properties. Well, an argument like this should convince you that mass really, really, really doesn't become bigger if you see it with high velocity with respect to you. Mass is an invariant. It belongs to this series. For people who want to dig a little deeper, we're not going to here. You can worry about questions about gravitational mass versus inertial mass. Different story, we can talk about it later. It simply doesn't happen. Now, why do people say it? Because you might still find it in some books. I'm not saying it to say bad things about other texts, it's because in many experiments, what you measure when we say that we measure mass is that we measure momentum transfer. Something bounces against you, and because of conservation of momentum, the bounce is going to make you move by a little bit. And by your momentum transfer, you can infer what the mass was. We will see in a moment that momentum actually does become bigger with high velocity. So sometimes, because people do measurements on a practical level of mass by momentum transfer, people are sometimes a little sloppy. That yes, momentum becomes bigger with high velocity, mass does not, but since measurement-wise it's sort of the same thing anyway, you might as well forget about the difference. Right? Particle physicists, when they measure mass, one way that they do this is by momentum transfer. So for all practical applications for them, it's good enough, the explanation, although it's not really true. Okay, all of this is just to point out mass does not increase with velocity. It's a fixed number. Okay, back to the main story. As I said, I have now a small catalog of numbers that do not change from inertial system to inertial system. So I can take these numbers, take this invariant statement that we saw in week 2, do whatever with it, with this statement, and as long as I use only these numbers, that resulting equation will also be invariant. And it's just a matter of algebra and playing around. So, let's do that right now. First of all, I'm happily going to multiply everything by m squared. It's still invariant, because the only thing I've done is multiplied with an invariant number, no problem. Next, I'm going to divide everything by d tau squared. That's fine, because hey, d tau is also an invariant number. So is this number. So multiplying with m squared, you would get this. Dividing by d tau squared, you would get that. M squared dt d tau squared, c squared. And you know what? For ease of notation, I will not write out dx, dy, and dz as separate entries. These three numbers together just make up Pythagoras theorem, and that's the same as if you would have written dx as a vector, x, y, z, squared with itself, the length of that vector. That's just for notational convenience, so I don't have to write down 4 terms every time. And everything is divided, so I end up with c squared, m squared. Still a completely invariant statement. Nothing wrong there. Okay. Here's my claim. Let's color code this. This number is momentum squared. To be shown. I will show you in a moment. Yes. That's momentum squared. This number is energy divided by c squared without the minus. Minus is still to be put in front. Those are claims. I have to justify that this is true. If it is, and again we will go through that in a moment, that this is indeed momentum squared and this is energy over c squared, then you can play around with this for a little bit, and you would end up with the following statement that E squared, this E, is equal to momentum squared times c squared plus m squared times c to the 4. That's this statement with my claim plugged in and then algebraically reworked. This equation many of you will recognize maybe from different courses. It's the energy momentum relation of particles and masses and objects in special relativity. It's an important statement. Again, we will still have to justify this, and we'll do that in a moment, but let's focus on the conclusion now. First of all, it's an invariant statement because we built it from an invariant starting point using only invariant numbers to manipulate. That's one. But also, it tells you that if you know the momentum of an object, and you know the mass of an object, you can tell how much energy is stored within the object. This is not exactly unlike as you would in normal relativity, normal mechanics, Newtonian mechanics, because there an energy of an object will be 1/2 mv squared or something like that. And that's also something like, well, if you know the mass of an object, you can plug it in there, you get the kinetic energy. And you might also recognize this as p squared over 2m if momentum is defined as n times v, same object. So it's similar, yes? If you know momentum and you know mass, you can calculate the energy. Already through Newtonian physics, I'm simply stating that's also true here, but the relation is different. Yes? It isn't. And I don't know, yeah, I know why he did that. It's because of the damn quantum mechanics. The Schrödinger equation starts with minus p squared over 2m, working on a wave function. Non-quantum mechanics people don't worry about it. But there's an equation in quantum mechanics, the Schrödinger equation, that starts with minus p squared over 2m. And it's that one that I accidentally, hello.
Oh, sorry. I'll be very late.
No, it's fine. I was just wondering if you're going to hand out something from the plastic bag.
No, it's fine.
It's okay. Put food in there? No, not too bad. So the relation is different, but the idea that there is a relation between P and M and energy is still true. And the reason that I put a minus there is just my muscle memory went into quantum mechanics and I shouldn't. But this, Newtonianly speaking, these are relations you might recognize. So it's still true, that relation is just a different relation. And that relation has immediate consequences. Again, we still have to do this part, but I want to focus on the conclusion for a second. One of them is, well, what if you take a particle that is not moving at all? Right? I mean, we have a situation, an equation that should be invariant. It should hold in all inertial systems. So if I have an object over here, actually here's an object, it just needs some kilograms, so there you are. And if I were to investigate what your energy is as seen by me, well, then it depends on which inertial frame I'm in. Because right now, with respect to me, you have a kinetic energy. So you have at least the amount of kinetic energy due to our relative motion. This is not relativity. This is also true in normal mechanics, that the amount of kinetic energy depends on how fast you're moving with respect to the object. So nothing new there. I also, well, I don't know, but you have a mass and you can use that number too, so on and so forth. But in Newtonian mechanics, if I were to choose a shared inertial system, so you and I are moving with respect to each other, then our relative velocity is 0, then your energy would be 0. And that is not true anymore in special relativity. Because the freedom that I have to go to any inertial system allows me to go to this relative shared inertial system, having a relative velocity of 0, meaning that we have a relative momentum of 0, but you would still have energy. And if you square root on both sides, you get your famous E is mc squared. So E is mc squared is sort of the minimum amount of energy that Joanna will have with respect to me. If I start moving now again with respect to her, fine. This number doesn't change because M is invariant and C is invariant. So you will keep that number, but you have some more too because now you and I have a non-zero P and that number is not negative. So E is mc squared, this famous formula by Einstein, says a whole bunch of things all at once. One of them is that every object has always at least that amount of energy. You can up that amount of energy by starting to move with respect to that object or person. You cannot lower it. So that's one thing that it says. It also says that if I am to be able to change M into a different type of energy, so maybe that's what I'm saying. M is a form of energy is what you're seeing here. Sure, there's a c squared in between, but the energy of an object is at least related to the object's mass, where in Newtonian physics those were independent numbers. Right? you could have an inertial system in which the energy did not contain a mass at all, namely the rest system of that. Here, every object has this minimal amount of energy stored. That means if you were able to extract it, you can turn mass into energy. Well, nothing new there. That's what you do in nuclear physics, right? Or more simply speaking, that's what you do in atomic bombs. You take the mass of objects, you take a little bit of the mass away, and you turn it into energy. It also says that energy, if I give you that number E squared, or E, and just that number, you cannot tell how much that energy comes from your momentum and how much comes from your mass. They're sort of stored in the same bucket, and you cannot tell which came from where. They're interchangeable. All of that is something that you did not have in Newtonian mechanics. So we have really new rules there. It's not just a formula, it's a new meaning of mass. It's the minimum amount of energy that somebody has stored in them, or an object has stored in it. And that as far as this number is concerned, you cannot tell the difference. Here's a stupid metaphor. Suppose that I actually would have a bucket here, yes? And I wasn't there to see it happen, but somebody came in with the garden hose and put some water in there. Okay? 5. But later it also started to rain, and some more water came in there, 7. And I just have a bucket filled with 5 plus 7. How much is that? Is that 12? Yes, thank you. That is 12. If I come in and didn't see it happen, I can tell from the bucket how much came from the garden hose, how much came from the rain. Right? They share together and form one big mix. And that's important too, because it tells us that just as time and space are related in special relativity, momentum and energy and mass also are related to each other. Yes. Final thing, M is invariant, C is invariant, so that means if you go to a different inertial system and then there the P goes up, E must go up with the same amount. So just as if you would go to a different inertial system, you would see the amount of time and space differ, but in a particular combination that keeps something exactly the same, namely the Minkowski line element. If you go to a different inertial system, the momentum might be different of the object, the total energy might be different, but always in such a way that M stays the same. It's really the same structure as the original guy, but what used to be time has now been turned into energy, and what used to be position has now been turned into momentum. But they share the same relationship to each other. Energy is different per frame, momentum is different per frame, but a particular combination stays the same, just as originally time and space did. Have you any question, Roger?
Yeah, I was just thinking how potential energy kind of plays into this.
Yes, that's a very good question. Where's potential energy? Well, potential energy is of course the special situation where objects are not left alone. Potential energy is just another way of saying something is pushing and pulling on the object. That means we have an interaction. That's next week's topic. So there is a potential energy question that I'm deliberately keeping to next week, but you are right. Okay, so lots of interpretation here. Oh, I cannot help myself. But final comment before we get through this. So T has started to play the role of, in a moment, what we call energy. Position has started to play the role of what we call momentum. Do you remember how you change time and space into each other if you go between inertial systems? There should be a very sound, resounding yes. Do you know a set of transforms maybe that turns time into position? It's the Lorentz transforms, right? Well, the fact that the Lorentz transforms is a thing that keeps this invariant, and we haven't changed it because we only played with invariant numbers, that means the same transformations must therefore also be true between E and P. So without thinking, I can immediately conclude from all of this that energy in a primed frame divided by C is gamma times the energy in the original frame plus or minus V over C times momentum. Might be a C off someplace. Right? It's mean this guy turned into that guy turned into that, so the same equations hold. And in very much the same way, we'll have this. Just your your Lorentz transforms, replace every e by every dt by an e, every dx by a p, and everything holds just as well. Check for the c's because I'm always messy with for me those are 1. I always have to think about units before I get them right. I'm happy to correct it in a moment, but the idea should be clear to you. So we've really found not just energy and momentum, but also how they relate to each other, and what it says about the relation between mass, momentum, and all that stuff, all that good stuff. So, but I still have to prove it. Right? What I have there in the blue and in the red, I still have to prove that that is the case. And we're going to start with the red one because that is the easiest of the two. So let's keep to my color code. Because my claim is that m times dx d tau, that is momentum. That's my claim. I have to show that that is the case. Well, it looks tempting to make that conclusion because, well, it's an m times a velocity, a distance divided by an amount of time. So it's m times velocity, and m times velocity in Newtonian physics is what you call momentum. So it looks momentum-ish. However, in Newtonian physics, if I want to know how fast something is moving with respect to me, what I have to do is measure how many meters it travels, and then check how many seconds that takes for it to travel the amount of meters. But I have to do everything from my frame, my x, my t. But that's not what we have here, because this is my x of something flying by, but the object's own time. It's the proper time of the object. So I'm sort of measuring the object's velocity by measuring how many meters it travels in my frame, and then ask that guy how many seconds there was in between that traveling. So I call this a bastard object. Bastard in the sense that you need information from 2 different frames. So it's more, this is why I say it's velocity-ish. So what I would really like is to have an object where I actually do end up with my amount of meters that I see the thing fly, divided by my amount of time that I see it fly. So that's not a tau, that's a t. And I still have the m over there. So this is what I would like, because this is what I actually would measure as my Newtonian momentum had I measured everything in my frame. So I have to make this connection complete. In order to do so, I'm going to need some formula that turns a tau into a t. I think all the way back to week 1.
dt is dan d tau.
Ends up over there.
Does it have to be 1 divided by? Or?
No, because d tau, gamma d tau, is a dt, but it's 1 over. So there you go. So what I have here is gamma times the momentum as you would measure it in a Newtonian system. This had been Newtonian physics. So there's momentum, and I put a little n below because this is what you would have in Newtonian physics. Again, I'm not using anything that I didn't know. I mean, I'm just using Minkowski line element week 2, plugging in a formula all the way from week 1. Now here we go. This object is by definition what you call the momentum in relativity. Newtonian momentum times gamma. That's what we got for now on. I'm going to call momentum in relativistic physics. So there's no physics in this equality sign, it's just redefining what we mean by the word momentum. Yes. Now if you do that, then indeed what I meant when I said that this was momentum squared, I meant relativistic momentum squared, Newtonian momentum times gamma. You might get a little iffy here that you say, but wait a minute, this is just a redefinition, are you allowed to do that? Well, yes. Because what we want from momentum is a couple of things. First of all, a momentum is something we want to measure in 1 frame only. So that necessitates that we do this step. That's one. This number, by itself, without the gamma, is really not measured by anyone because you need my amount of distance and then somebody else's time. So it means if you would ask me how fast is something flying by, I would actually not say this number, I would probably say that number. So why do we define it with a gamma in front? Because that's very important. Because this p, the relativistic momentum, is conserved. If two particles bounce into each other, then p will not change. This p will change. Newtonian p will change. This p will not. So if you want to do mechanics, and by mechanics we mean, for instance, that you want to see how things are touching and pushing and pulling on each other, one way of doing it is by doing conservation of momentum. That the amount of momentum before and after an interaction stays the same. That is not true for Newtonian momentum. It is true for that one. Later, when we're going to do the Lagrangian method, I will explicitly prove this to you. Right now, you just have to trust me that it's the case. So that is why we like to define in relativistic physics momentum in this new way, Newtonian momentum times gamma, because gamma is not conserved, right? Particles might have a different velocity after collision. Newtonian momentum is not conserved, but this combination is. And it makes it a lot easier to do calculations. So we prioritize that momentum definition over any other one. That's one. To be proven that it's conserved. Another way, reason why we call this momentum is because, well, if we were actually to measure something's momentum of an object, but an object is not flying very fast, then this momentum, it's Newtonian momentum divided by 1 minus v over c squared, that's me plugging in the gamma. If the object is not flying too fast with respect to the speed of light, and v is very small, that means v over c squared is ridiculously small. So you get 1 minus something very small, that's about 1. So that means if you go to everyday objects, cars, planes, you get back to Newtonian physics. And that's another something we want from our momentum definition. We are free to define things as much as we want, but the reason we do this definition is because this guy is conserved, that guy isn't, and because if you slow things down enough, you find yourself back in your high school Newtonian physics. So, there's that. So from now on, whenever me and the book and any article that you might read on relativity talks about momentum, they never talk about Newtonian momentum, m times v, they talk about gamma times m times v. Just keep that in mind. Okay, good. Curly thing. Curly thing for the non-Dutch people, curly thing means all correct. Let's move on to the next one. The blue one. Energy. E over c, according to my claim over there, let's write it like this, m times dt d tau, with a c someplace to be plugged in a moment. My claim is this is an energy. Well, how do I know that? Well, let's first observe that dt d tau is a number that we know. That's gamma again. That's the time dilation formula. So this is exactly the same from the work in week 1 as m times gamma. So there's that. Again, we call this number the energy, simply by definition. And that too sounds iffy, just as it was in the momentum before. So do you just get to call stuff whatever you want? Well, yes, that's our freedom, but if we want to be consistent with Newtonian physics, what we want is that this object, m times gamma, first of all is conserved, as it is in Newtonian physics. Right? The conservation of energy should be upheld if you want to use the word energy. And secondly, if you actually look at objects that go with a low velocity, it should actually give you back the Newtonian expression for energy. By the way, I'm going to plug the C back in there. left out the C there. So I'm looking at this object now. Okay. So we're going to call this guy the relativistic energy, and I'm going to justify that definition to show first of all that it goes to the second, then it goes to the expression that you already knew from Newtonian physics if you go to low velocities, and in a moment I will show you that it is conserved. Yes?
Why C squared? Energy C?
I might have messed up a C squared over there. Let me check in a moment. Yes. Was that your question too? This is me being so used to C being 1 that I don't usually look at the amount of squares. By the way, we can easily check for ourselves because the units of every object should be the same. So this should be kilogram squared times meter squared divided by second squared. That should also be the case here, which it is, because it's kilogram squared meter squared divided by second squared. Sure, proper times seconds, but seconds is still seconds. What do we have here? This is unitless. Kilogram squared meter squared divided by second squared. Looks fine to me. So far this part is still correct, unit-wise. How are we here? What's the unit of an energy?
Short line meter squared or second squared.
I think it's this, yes? That's the unit of an energy. This whole object should in totality be kilogram squared meter squared divided by second squared. Oh, it was just energy all along. I have to put the C there. Okay, that should solve your problem and yours. Again, this is me being used to putting C as 1 and only plugging in the correct place of the C later. This should be fine. Continue there. So my statement is that m times dt d tau times
I think you were right, Gideon.
what?
I think it is E over C.
It is over C. Help me out here.
Because that's meter to the 4.
Yeah, it's E over C squared. And if you get rid of the squared,
Yeah,
then
you're
the
right.
C is figure out.
Okay.
So, but it should be E over C squared.
This in this totality should be E over C squared.
Yes. Then the E becomes
Yeah,
E
yeah,
over C
because
is
it-
1
yeah,
C,
you're right,
and then your
because
C gets back.
Over here I put the C back into the
Yes.
square and now it should be fine. Okay. Again, this is why we put C equal to 1, yes? Not to have this issue. We should be good now.
My thing was more that the mass isn't squared anymore, the dt of d tau isn't squared anymore, but the C is still squared. If you go from the left part to the right.
E over C equals C. So the E, if you bring the C to the other side, it's C squared.
I think it's correct. What we have here.
Alright, yeah, that's fine.
Okay, but then my claim still stands. My claim is that this object, you're right, Brecht, so putting myself up with these squared that I over there did not put within the brackets, but anyway, we're fine now. Okay, my claim is that this is an energy, and here was the reasoning as we were also having with the momentum. In order to justify calling this thing an energy, we have to show two things. First of all, that it is conserved, that it doesn't change in an interaction. Secondly, we have to show that if you go to low velocity, so you're back in Newtonian physics, you should get back the expression that you know from Newtonian physics. Then you have a correct definition of energy. So let's write out what we mean by gamma. mc squared 1 minus v over c squared, square root. And we're going to go to low velocities now. Yes? Just to show that we get back to Newtonian physics. Well, if you go to super low velocities, where v is pretty much 0, yeah, sure, then you get mc squared, fine. But let's make velocities low, but not that low. That allows us, if we use this famous formula, we're using a little mathematical trick here. If you have 1 plus x to the power n, but x times n, that combination happens to be very small compared to 1, then this is an extremely good approximation. If people want to prove this, it's what you call a first order Taylor approximation. If you want, we can prove that, but that's not my goal here. This is mathematical fact. It works as long as n times x is very small compared to 1. But Rx in our case is not just V over C, it's V over C squared. So that happens to be ridiculously smaller than 1 in everyday circumstances. And N is, well, minus 1/2, right? It's 1 over square root. So that means what I will get is 1 plus V over C squared times 1/2 by good approximation. The smaller V, the better it works. If you multiply this out, you get mc squared. Fine, that's what we already knew. Right? If you don't move at all, you have at least that amount of energy plus extra. And the plus extra in the small velocity one, well, the c squared here and there are going to cancel each other out. What you end up with is 1/2 mv squared, which is the kinetic energy from Newtonian physics. So this object, for low velocities, actually becomes what Newtonian physics already told you all along. Yeah, sure, plus this extra part, mc squared. Let's check your Newtonian physics understanding. What's the 0 point of energy? Rephrase the question. If I take an object's energy and I add 1000 to it, so just whatever the energy was plus 1000. But I do this for every energy measurement that I do. I always add 1000. This will not change your Newtonian physical outcome. Because if you want to do physics in Newtonian way with energies, what you do is look at the energy before, look at the energy after, and the difference in energy is what tells you how fast things have started to move. It's the differences between energies in Newtonian physics that you care about. But, so that means if you have the energy before and you've added 1000, but the energy afterwards got the same 1000 added to it, their difference is the same as if you would have never added to 1000. So Gerco, if you follow the course in classical mechanics, might have said that there's no 0 point of energy. You can define it at will. It will not change anything. Yes? Because in Newtonian physics, the only thing that gives you measurable outcomes is the difference of energy before and after a process. So if you up the amount of energy consistently with 1000 or minus 500 or 1 million, whatever number you've upped everything is going to drop out and taking the difference again. So measurement-wise, you will never see this difference. So as far as Newtonian physics is concerned, that guy was never there. You won't measure it ever. And then we're back in Newtonian physics. So what we have is that this object that I claimed is energy, at least in Newtonian sense, indeed is energy. It also has to be conserved, that it doesn't change in time. Conservation of energy. That's what we're going to prove, Brecht and myself, with you guys in the tutorial this afternoon. So it's more than just, it sort of looks like Newtonian energy if you go to low velocities. It has all the properties of it, and it justifies, from this moment on, calling it the energy. Yes?
So, are you saying that the Newtonian energy or the relativistic energy is conserved? Or both?
That's a good question. Is the Newtonian energy conserved or is the relativistic energy conserved? It's a relativistic one.
Yeah, so it's M gamma.
Yes, this guy is conserved.
Yeah, like the previous one.
Exactly, just like the relativistic momentum is conserved. Both these statements are to be proven. We will do that with Lagrangian physics, and Brecht and I will walk you through it during this tutorial. So from this moment on, every time that you read the text on relativity, or in this class we talk about energy, we will always mean this object, the relativistic energy. And yes, there's still the question, well, what about potential energy? That's what we have next week for. Okay, another curly thing. That means these two claims are now complete. That means the whole thing is now full circle now. So takeaway message, started with the invariant Minkowski line element, used our catalog invariant numbers, got this expression, itself invariant, and energy and momentum play by exactly the same Lorentzian transforms as time and space. We only have to prove that indeed this is momentum and that's energy, and that's what we've now done. Except for the part where we have to prove that they are conserved. Yes? That rounds up the story. Alright. Now in the exercises to make before Friday, we have a bunch of exercises where you get to play with these expressions. So just as we were doing before, that you said, oh, there's something flying by, how much time did it take for so-and-so, how much distance is the travel? You now get to do the same exercise and saying, well, okay, in this frame it was this many joules, and how much is in the other frame, and the amount of joules in the one gets transformed into momentum of the other. You can play around with that. Oh, I cannot help myself. If this is true, and 2 weeks ago we used the Lorentz transforms to construct the Minkowski diagrams. Right? These two we use to get x, ct, and x prime and ct prime 2 weeks back. Okay. Momentum prime, energy over c, energy prime over c. Same line element, same Lorentz transforms, same Minkowski diagrams. For the philosophy-minded people, note that there's a deep connection between time and energy and momentum and space. That is what you see here. They play by exactly the same rules. Quantum mechanics people, what's the uncertainty relation between momentum and position? Delta x, delta v, so and so? H bar over 2. So quantum mechanics says you cannot measure momentum and position with infinite precision. Okay, well, position becomes momentum, time becomes energy. So using the same trick, you immediately get that there's also a certain relation between time and energy. You cannot measure time and energy all at the same time. And our particle physics friends make use of that all the time. Because they take a vacuum, there's no energy in there, but there is energy uncertainty. That means quantum mechanically there's 0 plus or minus a little, and the plus or minus a little, that means you can make a particle out of that. But then the amount of time says, yeah, but the amount of time cannot be too long. Those are what our friends, Katie, Jacco, Marcel call virtual particles. Particles pulled out of the vacuum because the energy momentum relation of Heisenberg that we get directly from using this time energy and position momentum relation. Okay, so far so good. This is the main learning goal as far as energy momentum is concerned. Again, exercises to be done in tutorials, but I promise in our remaining time to also talk to you about a new type of formalism. Yes?
Why, if we only use invariants,
Yes.
do we get energy and momentum out of it, and those aren't invariant?
I think this is a good question I think I would like to share with everybody. So we use only invariants, and yet you say, but we get something that is not invariant.
Yeah.
How are things not invariant?
A difference in different frames, right?
Yes.
Yeah, isn't that the definition of invariance?
I very much appreciate this question. If I can paraphrase, and I'll add on something that you're not asking, but I think is also worthwhile repeating.
Before you do that, the camera's looking at us now.
That means somebody over here looks a lot like me.
Or a horse.
Well, you take your pick which one is the bigger compliment. That is interesting. How long has it been doing this?
About 30 seconds.
Oh, wait a minute. Just maybe because she walked out and then I said, oh, there you go. And let's say that was a person that is identified as such. Okay. Well, let's see, but thank you. I did not pick up on that. Yeah. My statement is not that energy is invariant and the momentum is invariant. They're clearly not. They play by their own Lorentz transforms. And this is already true in Newtonian physics because, again, the kinetic energy between you and me is 0, but in the other frame it's non-zero. So the non-invariance is already to Newtonian physics. But my claim was not that momentum is invariant or that energy is invariant, but their relationship is. This formula is invariant. So if you go to a different inertial frame, it's not as if you have to plug an additional number 5 here to make it work again. The formula stays the same. No, this is an extremely important question. There's a nuance there. Are numbers invariant, or is the relationship between the numbers invariant? What I meant is the relationship is invariant, the numbers are not. See? Okay, I got it. It would be worse if the thing actually starts walking behind the person who came by. Fortunately, Skynet is not that evolved yet. So is that a clear difference? The formula itself is invariant. The law of physics is invariant, although the numbers are not. That was the same already in the Minkowski line element all the way back in week 2. These numbers individually are not invariant, but their combination is. Same here. Now here I'm going to add out something that you did not ask, but I feel like mentioning anyway. Over here we claimed, didn't prove it yet, that the relativistic momentum and the relativistic energy are conserved. By which we mean that they are constant. By which we mean that before and after some interaction with the rest of the world, the number has stayed the same. Do not confuse that with invariance. Invariance means that whatever the number is, it's the same in all inertial systems. Constant simply means in one inertial system measured now in a few seconds or an hour or 5 years later, the number has not changed. So, long story short, energy is not invariant, but it is conserved. Momentum is not invariant, but it is conserved. The relationship between momentum and energy is invariant and conserved. Okay, no new physics now, just a new mathematical formalism. And this is going to be a short introduction. You can have a whole course on it, which I wish we had at MSP, but that's a different story. We're going to introduce now the Lagrangian formalism. No new physics, again, old physics, new mathematical way of writing it. The Lagrangian formalism, for the people not in the know, is a way of doing mechanics. And by mechanics I mean how does one piece of physics interact with the rest. That could be pushing and pulling as in Newtonian physics, it could also be light, it could be electric fields, it could be quantum fields, whatever. Just some piece of physics trying to talk to another piece of physics, how does one do that? In non-Lagrangian physics we know how to do that depending on which field it is. If it is pushing and pulling, fine. You take Newton's laws and you apply it. If it happens to be electromagnetism, you take Maxwell's equations and you apply it. And if it happens to be, I don't know, optics, you take the laws of Snell and reflection, how light rays interact with lenses and mirrors, etc. But that makes every part of physics have its own little island of formula, so to say. But then smart people figured out that, wait a minute, there's an underlying formalism that is true for all of physics. That's Lagrangian formalism. So I'm going to be very abstract for a moment, and then I'm going to be a little bit more specific by an example. What does Lagrangian physics say? It says that one has an object, L, a mathematical function, called a Lagrangian. The Lagrangian is highly dependent on which piece of physics you happen to be looking at. If it's mechanics, the Lagrangian looks different than if it is Maxwell's equations, it looks different from optics, so on and so forth. But the Lagrangian should depend on whatever is going on in that part of physics that you happen to be looking at. If it's electromagnetism, then clearly it should depend on electric fields, magnetic fields, for instance. If it's mechanics, bouncing and pushing of particles, then there should be the positions of the particles built into it. I'm going to specify now for the special case that you have a piece of physics where one can identify the position and velocity of particles. So right now, me writing down this function Lagrangian of x and v means I'm at least looking at a part of physics where particles or positions and velocities can be identified. this does not work for electromagnetic fields, for instance, because magnetic fields don't have a single position, they're spread out. That's okay. You can also write down Lagrangian with an electric field and its velocity. But I'm specializing now to the case where we're interested in, namely particles, spaceships, touching, pushing, and pulling on each other. Then whatever the Lagrangian is going to depend on the position and the velocity of the objects within it. Now, if you have a Lagrangian, then there's an extremely deep rule of physics. This is that deep rule that connects all of physics all together. That connects all the little islands of the different fields. There's a deep rule in nature that is called the principle of minimal action. Just curious, have people heard about this before? Some places I see some nodding, yes? I see some shaking of heads and some blank stares. Okay, that means I have some more explaining to do, otherwise we could I'll just stop now. The principle of minimal action is a rule of physics that says the following. If you take the Lagrangian of your system, your piece of physics that you're interested in, L, and in our case it depended on the position and velocities of his constituent actors. And you would integrate it over time, right? Lagrangian is a function, you can integrate it, that means a number will come out. If it is a definite integral from value 1 to a to b, some number will come out. That's what integrals do. They turn functions into numbers. That number is what we call the action, called S. Here's the law of physics. The law that connects all of physics all together, all of the universe. It says nature will choose the function where particles are and how they move. X and t are functions of time. Particles are different positions, different velocities. It will always try to make this number, the action, as small as possible. Yes?
Do you know why?
Yes.
Yes.
When people
Because we talked about it in particle physics with Jaco, and then he told me to ask you because he didn't.
Oh, Jacco told you to ask me. Okay. Thank you, Jacco. I was going to have a stern talk with him. Because in particle physics, they use this. You do particle physics, they don't use Newton's laws. This is much easier. You have to get used to it because all kinds of new words and everything, but it's much easier. But Jacco has told you that this is true, though.
Yes.
Okay.
Can you tell me why?
Let me reserve that one for a moment. I cannot help myself. Jacco knows this evil person. It's because in quantum mechanics, because of the Heisenberg uncertainty relation, particles are never at the definitive position and with the definitive velocity. If they were, you would break on Heisenberg's uncertainty relation. So that means that x is really x plus or minus a little, and v is plus or minus a little. That means if you would integrate this, then the plus or minus option of the one and the plus and minus option of another way that things could have done are going to cancel each other out. I'm saying something very deep here. It's not part of this course, but because Jacco told you to ask me, evil person, is in quantum mechanics, things are wavy. There's a probability distribution, and waves can cancel each other out. So Heisenberg uncertainty relation says that this is an x and a v that are not specifically defined. They don't have a fixed position and velocity. So instead you have to write them as waves, but waves can cancel each other out. If one wave goes up and the other wave goes down, it net becomes zero. And the quantum mechanics says that the probability of finding the particle there, where the waves cancel each other out, becomes very small. So if you allow Heisenberg's uncertainty relation and you plug it in here, and you look at all the waves, then you find that many of all the waves together are going to cancel each other out. The plus of the one is going to cancel the minus of the other. And what remains, that's just a mathematical exercise, is the wave for which this number is smallest. So it's quantum mechanics that says that the smallest number should come out. It's the cancellation of the waves.
You didn't just say that. You just made me ask you. Made me wait 4 weeks and then ask you.
Okay. Here's the cool thing, ask him back. And then, yes.
So the fact that this integral gives the smallest solution was derived from quantum mechanics and then applied to other branches?
No, historically it went differently. Lagrange, that was a guy, found that if you took Newton's laws, then Newton's laws could be recast in this form where the fact that you knew that the answer should agree with Newton's laws predicted that gave it as the smallest number. And then when the Lagrange, the guy said, well, if this is true for Newton's laws, then I'm just going to promote this to a general rule for everything in physics. And it was only later, Lagrange found this way before quantum mechanics was invented, it was only later that people found, oh, by the way, with quantum mechanics we can prove Lagrange's postulate. So it was derived from Newton's laws. There you can make this extremely specific, and then promote it to generality, and then later quantum mechanics proved the generality. Okay, so going back to the main story now. I feel like I was put on the spot by Jacco. The stern talking to is warranted here. Yeah, it's very important that you understand what happens here. If I were to do mechanics here, I would look at, I don't know, I typically take a flying pen. I throw my pen around and I want to see how it flies, so what is its position and what is its velocity at a moment in time. Well, if it flew in a parabola shape, then this is a parabola and this is its derivative. And because the functions for parabola have a particular form, that means the outcome of this integral is going to be some number, 17 or so. If, however, the pen would have flown not as a parabola, but maybe as something more complicated, maybe more stretched out hyperbole or something like that, then x and v will be different functions. The number will be different. The outcome of this number that we call the action, maybe now it's not 17, it's 200. And there's an infinite many ways that this number can come out depending on how the pen was flying. And this rule now says, no, of all the ways the pen could be flying, nature chooses the one that has the smallest outcome. And that's what the nature follows. And again, the reason at the very deep level is quantum mechanics. So, that means if you want to know how pens are flying, then what you have to do is write down the Lagrangians for flying pens. I'm going to talk about where you get it from. I'm going to talk about the Lagrangian for flying pens. Plug it in here. Try every single x and v combination. Do the integral, get all the infinite amount of numbers, and choose the one that is the smallest. That's the way that the pen was flying. That's a crappy and long exercise to try every single combination until you find the smallest, yes? So fortunately, that's a mathematical exercise. I will upload the proof. You don't have to memorize it, but if you want to go through it, you can. This is solved. If somebody gives you a Lagrangian and you want to make this integral as small as possible, somebody, Euler, found out the formula that makes this integral the smallest. Again, proof I will upload if you're interested, but the trick is as follows. You take a Lagrangian, you take its derivative with respect to x, you can do that, it's a function of x. Then you also take your Lagrangian and take its derivative with respect to the velocity. You can also do that because the function depends on velocity. But of this guy, you then take the time derivative. You now have an equation. Given a Lagrangian, you can plug it here, you can plug it there, you get an equation. That equation dictates what x and v are such that this guy is the smallest. So you can now completely forget about the intermittent step. If somebody gives a Lagrangian, just plug it in here, whatever comes out, that's the thing that makes the action smallest, that's the thing that makes nature go. This equation is called the Euler-Lagrange equation. Euler because he found this equation, Lagrange because it's based on Lagrangian physics. Okay, this is an extremely quick introduction to Lagrangian physics. How does one do it? You have to get yourself a Lagrangian describing your piece of physics. You want to know how things go in that piece of physics. be it magnetism, electricity, light, whatever, mechanics, just take a Lagrangian, plug it in here, whatever comes out, that's what nature does. There's a lot more that can be said here, but let's stick it to here. Mind you, on an abstract level, this is not different from what you were doing all the way back in high school when you were doing normal Newtonian mechanics. Because somebody gave you an F, a force. It comes from the outside because your teacher told you or your book told you. You took that F, you plugged it into an equation, namely Newton's second law, and that told you what nature did. We have the same here. Instead of being given an F, you're given an L. And instead of plugging it into Newton's second law, you plug it in Euler-Lagrange. You solve it, you get the solution. So we're not doing too much different from what you were doing all the way back in high school. It's just that the thing you're given and the thing that you plug it into are now different, but it gives you the same outcome. People like Newtonian physics a lot better because those F's, so to say, the pushing and pulling is something that you are used to as a human being because you know what pushing and pulling feels like. Right? It feels like a natural fit with your everyday experience. Lagrangians do not feel like a natural fit. I cannot touch or feel or push or pull on a Lagrangian. But it's the same mathematical structure. The proof from here to here is the same as from Newton's laws. So it really is just a mathematical recast of Newton's laws, but in a way that doesn't agree much with everyday experience, but it is mathematically exactly the same thing. That was how Lagrange did it back then. Now, why do people then use this trick if the one that we already had by Newton feels more organic, although they're mathematically equivalent? It's because in Newton's laws, I give you 3 reasons. In Newton's laws, the forces are 3-dimensional. Maybe not on a high school level, but forces can push and pull in 3 directions. If you're really unlucky, your force itself pushes and pulls in 3 directions, like the Lorentz force, right? The magnetic field and a flying particle, the force is perpendicular to both. That means in some cases you have a 3-dimensional problem and you have to use the full power of vector calculus to solve it. However, a Lagrangian is only 1-dimensional. That means the resulting integrals, the mathematics is much easier. It automatically will take care of all 3 directions all in one go without ever you having to do something complicated like vector calculus and worrying about this direction versus that direction. It makes it much easier. That's one reason. Second reason why people use Lagrangian physics is because this formalism, we've now used it for particles that have positions, but again, I mentioned this rule is applied in other places as well. You don't have to jump from one island of formulas to the next island of formulas every time that you go to different physics type. This trick is upheld by all of physics. So it's one formalism to rule them all, so to say. Yes? Dutch people, you don't have to flip through your binas. Yeah, you know what I'm talking about. It's a booklet that the Dutch students in physics get that has all the formulas. It has one table of formulas for optics, one table of formulas for mechanics. You have to jump between tables if you want to do different types of physics. Not here. The binas will be one page, this page. Second reason. The third and most important reason to use Lagrangian physics is because it immediately proves to you if energy and momentum are conserved quantities for any system, whatever they are. Yes? Energy is conserved. You either know this because somebody told you or by measurement. Lagrangian physics proves it mathematically rigorously. And I will write down the expression for the energy that you get if somebody gives you a Lagrangian. Energy. If somebody gives you a Lagrangian, you want to know the energy of that system, is given as follows. You take the Lagrangian, take the V derivative, multiply that guy by V again, and then subtract the Lagrangian. This is the energy of any system in nature. You don't have to look in your binas or whatever booklet you have. Well, what did people find for the energy of this system versus that system versus that system? If somebody gives you a Lagrangian, Plug it in there, you get the energy of that system. And more than that, you can prove, that's an exercise that Brecht and I will do with you guys today in the tutorial, is that if you take the time derivative of this energy, it is always zero. That's a proof. It's mathematics. No matter what the Lagrangian is. Now what does it mean if I say that d e dt is zero for any Lagrangian? What does the e dt is zero mean? Energy doesn't change. The conservation of energy. So this statement here is not just that if somebody gives you a Lagrangian, you know immediately what the energy is of that system. The fact that this is always true for every system, for every Lagrangian, as Brecht and I will go through you in the tutorial, tells you that the conservation of energy is proven for all of physics, all in one go. So that's the third reason why Lagrangian physics is useful. If you have Lagrangian, you know not just what the energy is, you know also that it is conserved as a mathematical fact. Not as somebody measured it, or if you do this experiment versus that experiment, no. It's a mathematical consequence. So in theoretical physics, people exclusively work with Lagrangians, and that's probably why Jacco used it in his courses. One glaring point is now missing. Where do you get the Lagrangian from? I'm simply stating there is a Lagrangian for every piece of physics. So in our final minutes, let's write down the Lagrangian for relativity. I will copy and paste this here. So, one more time to summarize, what do you get from a Lagrangian? Somebody gives it to you. Over here, you get how nature behaves. You follow this arrow. If you want the energy and it is conserved, follow this arrow. E equals dl dv minus L. You have everything that you need to know about the system. The only thing that you need is to get the starting Lagrangian for whatever physics. Where do you get it from? Well, that's highly context dependent. Clearly for electromagnetism it's a different thingy than for mechanics, as it is for optics. Let's guess our way towards it. Here's the action. Do you remember the principle of relativity? Not just the words. Do you know what it means? Every system is preferable, dictator, something like that?
There's no preferred system.
Oh, there's no preferred system. Yes, thank you. Every inertial system must be equally good to get the same laws of physics out. Again, to Guus's question, not the same numbers, but the law should be the same. Well, I get my law of physics from minimizing this integral. That's this part, yes? So if I want to have some laws of physics that behave the same in all inertial systems, I better choose the L in between to be determined, but I better choose it such that the action, the number itself, is an invariant number. If S is not an invariant number, it is a non-invariant, the smallest number in one frame is probably not the smallest number in somebody else's inertial frame. Give you different laws of physics in every frame. That's against the principle of relativity. If I want to get the same laws of physics in every frame, I better choose my L such that this integral doesn't change when you go from one inertial frame to the other. That gives us an extremely strong clue what L should be. Well, you have to integrate over time. Is time an invariant number? dt. It is not. Lorentz transforms, time dilation, so on and so forth. Are there any other numbers that we know are invariant? Well, it's easy. Okay, so if you want laws of physics to be the same in every inertial system, you want the action to be the same in every inertial system. This is not invariant, so you better choose L such that the totality of the thing is invariant again. What if we are able to turn this into a d tau? That will work, because d tau is invariant. So if I can choose my L such that my dt turns into a d tau, then I'm going to have a Lagrangian that's invariant, giving the same laws of physics. I will get something that the laws of physics is going to be the same in our inertial systems. I uphold the principle of relativity. Is there any way we can turn dt's into d taus? Week 1 or so.
Gamma.
There's a gamma. But in this case, it's 1 over gamma, yes? Okay. So long story short, that means simply from the principle of relativity dictates that the Lagrangian that we need if you want to do special relativity must be 1 over gamma. We have no choice in the matter. That's the only way you can turn a dt into an invariant number. So I said we're going to guess it. No, it's dictated by the principle of relativity. Any other Lagrangian will not uphold the principle of relativity. So this is the one that we need. This is where we get our Lagrangian from. We're going to wrap up in a moment, but this should be clear to you. The only thing that I'm going to add to this is that, well, 1 over gamma, let's be careful, 1 over gamma is not invariant because it contains a v, and v is not the same in between inertial systems. But this combination is. Okay. But from the catalog over there, I can also multiply this with c's and m's as much as I want because those are invariant. Yes. Now it simply becomes a matter of convention. Lagrangians are defined as objects as having the same unit as an energy. That's a human definition. You don't have to do this, but out of consistency, we've decided to all these little islands of physics, they'll always make Lagrangians an energy number. 1 over gamma is not an energy, it's unitless. So if you want to make it an energy, but you want to keep the invariance, you only get to multiply it with c's, m's, or d taus. But in that combination, that the thing becomes an energy again. Then 2, you have only one option. It's mc squared. And again, this is a matter of convention. We define it with a minus sign. Don't worry about that. The minus sign again is a convention thing. The physics will not change. For the following reason, first of all, the minus is not going to change in invariance. Minuses do not change between inertial systems, so you're allowed to put it there. But more importantly, the reason that we put the minus in there is because if you're now going to plug this Lagrangian into these equations, right, to tell you how physics goes, the minus is going to end up here after derivative taking, but also on the other side, so it's going to drop out anyway. So laws of physics-wise, no matter if you put a minus or a plus there, it doesn't matter, you will get the same laws of physics. It's simply out of historical convention that we've happened to have chosen the minus. So I'm not changing any physics, the minus is going to drop out at this level. And with this, simply by knowing our principle of relativity and knowing a little catalog, we have found the Lagrangian of special relativity. This is an exercise that Brecht and I were going to do, but if you're going to plug this guy into there, guess what you're going to get? We had an expression for energy before, from the Minkowski line element. Right? If you have a Lagrangian, you plug it in here, you're going to get the energy. You might not see it on the spot because it's a little exercise in derivative taking, so on and so forth. So I'm simply telling you, Brecht and I will go through the exercise. Plug this guy into there, the outcome is gamma mc squared. And that's exactly what we found before when we did it using the Minkowski line element. So in this way, with the Lagrangian formalism, we're going to completely reproduce all of it that we had here. And just to wrap up, we should have expected nothing less. Because when we did all the work here to get energy and momentum, we used it from the Minkowski line element, which was invariant. Yes? We built these expressions that we got on this side of the board from the invariance of the Minkowski line element. Sure. We did the same thing here. We use invariance of special relativity, so clearly the energy should come out the same, and they do. So with that, we're going to wrap up. The Lagrangian formalism is what Bert and I are going to work on with you in the tutorials to get a little bit of a better feel for this, but we're going to prove, first of all, that this is true, and this statement that this guy is the same, doesn't change, conservation of energy for all physics throughout the universe. And with that, we'll see you in the tutorial.